Okay, hello and welcome back, everyone. So we're moving on to section 3.2, and this one should feel a little bit more concrete. It should feel a little bit more like regular math compared to the last section. Last section, I think, is really fantastic if you're taking this course in any sort of applied setting where you're going to go off and be a biologist, you're going to go off and be a physicist, an engineer, computer scientist, etc. I think that last section is the best one for just applying calculus to the real world. Even though you didn't see much of actual calculus there, you really only saw that definition of dynamics. But it's such a beautiful checking point to make sure that the models you've constructed can really predict the future, or at least have the ability to predict the future. And also it describes so purely how we do try to predict the future in math. But today we're actually going to get into, okay, where did all those dynamics arise from? And not even all of them, right? We're gonna find a very specific subset of models which we can construct based on some sort of physical reality, and then find the solution to these models. And the solution to the models are going to satisfy the definition of dynamics from the last section. But really what we're focused on is looking at the models themselves and solving them, and you're going to find out that regular calculus, the calculus you know and love, is actually what's going to show up today. It's not going to be that kind of abstract ideas of dynamics we had in the last section. So we're going to start with something called the continuous initial value problem, and I'm restricting this to one dimension as always. And what I'm going to really call this is the initial value problem for integrals, and I'm going to use the term IVP. A lot of mathematicians will as well, IVP for initial value problem. And here I'm saying it's for integrals. You could also call this like a continuous initial value problem, like I say. This is going to be a dynamics, and if we recall from the last section, how do we like to think about dynamics? We like to think about dynamics as utilizing two pieces of information about the real world. And we like to utilize the state we are currently in, as well as a rule which describes causality. And that's exactly what the initial value problem for integrals does for us. So it's always going to be paired, and at least the way that I present it, it'll be paired with the curly bracket on the left. So it's going to be a set of two equations where the bottom equation tells me where I start. So if I look at the x here, this is where I start. If I look at the t0, this is when I start. And the right-hand side, it's a piecewise function, right? So it's just saying my time is equal to where I started, to when I started, I guess. And so that's all describing the state that we are currently in, right? The second piece of information I need to predict the future. If I look at the top row, this top row is going to say, well, the change in my state, also known as a derivative, the change is equal to a function, right? And that change is going to be equal to a function. How does time behave? Time is after, right? Or greater than. That's why I've got the greater than symbol there. So time is after when I start. This is the initial value problem for integrals is phrased as the following. It's also known as a first order linear ordinary differential equation. So I've got all those fancy words in there for you. If you're ever curious as to what people mean when they throw around that word differential equation, that's what we've got here. But really we should think about it as a set of two equations which describe when I start, where I start, as well as the change in my state being equal to some function. And that change only applies after when I start, right? It's going to describe how I change in the future. We give special names since these are initial value problems. We give the time t0, the name the initial time, and the place or just value x, the initial value. That's why we call it an initial value problem, because this is the initial value, and I guess we're solving a problem. Integrals, of course, will show up when I find a solution to this. So how are we going to find a solution? Well, if I've got a derivative and I would like to solve for, y, in some sense, y is the quantity I would like to predict. If I want to solve for y and it's got a derivative on it currently, well, how do I take an antiderivative? I'm going to do that with an integral. And so here we see the integral. I'm basically just integrating both the left and the right-hand side in the time variable to get the answer. But in particular, how do I make sure that my answer fits the initial value x at specifically the time t0? That's where kind of this special x is. X is playing the role of my plus c in my integral. So that's why I have a plus x there. And then how does that initial time t0 fit into everything? Well, really we should think about this integral as an integral which starts at our initial time and it ends at wherever we are today. So that's what's going on here. The integration begins at the initial time and ends where we would like to predict the future. And so the integral ends at the time t, t being the input to our solution. And so really up here, I've written it as integrating in dt, but down below, I've switched the variable of integration to this variable s, just so that I could save t in that upper bound and put t in y. So you'll notice we changed that variable to an s. Not a big deal. It just means that, I can save my t variable for another reason. Anyway, that's going to be the solution. And so really what I've just circled is exactly 1/2 of what you should memorize for today, or really, if you start here, the solution is down here. So that's really one of two things you should memorize for today, the solution to the initial value problem for integrals. And of course, we call it for integrals because we have an integral here. Let's actually see some examples of this in action. I'm going to skip over that it is a dynamics. You can verify for yourself that it is indeed a dynamics, as our previous section defined a dynamics. Let's look at some examples of these, because I think that's what we want to learn about is applications of all of these. First example is going to be the area under a curve. Not really surprised there that the integral is going to compute that for us. But I want to phrase the area under the curve in the perspective of dynamics, because I think if we can make this perspective shift that calculus, being both differential and integral calculus, can be applied so much broader than just the area under the curve. If we interpret everything as a dynamics, we can in fact fit the entire area under the curve set of calculus underneath the umbrella of dynamics. So let's just think about a function f as some curve we would like to know the area under. And in particular, let's suppose we want to compute the area over an interval t-min to t-max. How could we use our interpretation of initial value problems for integrals to compute the area? Let's pretend, this is what I said at the top, let's pretend we don't know that a definite integral computes the area, right? So completely forgetting that we already know that it computes the area, let's just pretend we want to try to come up with the area from scratch. Let's think about this in terms of the initial value problem. So let's recall the initial value problem always has this curly brackets on it. And we have both a prime, we've got a derivative of whatever we're looking for, as well as where it starts, right? So this is how does the area change? That's what derivative means, right? And where does the area start? That's what the initial value means. Well, if we think about where it starts, let's say we're just going to compute the area as over some interval starting at t-min. Here's my plot, right? And then maybe let's say we start at t-min here. Let's put t-min in here. What is the area under the curve over the interval t-min to t-min, or wherever it starts? Well, it's going to be width times height. The width of that vertical line is going to be 0, and so my area is 0. So what we can say about the initial value is that the area starts at 0. But how does the area change, right? I think that's the important thing here. So we ask a question about how does area change as, and I'm putting time in quotes here, time evolves. Well, if we think about it, if we move forward in time, so we're going to take that t-min, we're going to shift it forward, it's going to add some area here, right? It's going to add this thing. It's going to add that line I just drew. That's how I'm going to add that much area over time. Well, what did I just draw? I drew the height of the curve. The height of the curve is how the area changes as time evolves, which means there's my area changing. What is the height of a curve? Well, the height is just the y value. The y value is just the function itself. And so what we have here is an initial value problem for integrals where we have the area at t-min has to be 0 and the change in the area has to be the height of the function. If I go ahead and go back to my solution here, if I put an a there for area, a at t-min here, and that has to be equal to 0, I'm plugging in 0 for x, I'm plugging in t-min for the lower bound on t. That's saying that the area of the interval 0 to t is just the integral of f of s. That's exactly what we know from calculus, but we've discovered it from thinking about area as a dynamics. And so that's what I've got down here as well. I'm just saying, once again, we start at 0, the change is equal to the height of the function. And so what does that solution look like? Well, it looks like the integral from t-min up to some future time t. Well, it's just going to be the antiderivative from t-min up to t, or as we all know and love, capital F of t minus capital F of t-min. And so we've just proven the second fundamental theorem of calculus, thinking about this in terms of dynamics. Very, very cool to think about it that way. I've got maybe a different interesting application here, which is going to be extracting position from velocity, something you may have done in Calculus 1 as well. But let's suppose that we're given a proposed flight velocity for a specific airplane flight between Rutland and Boston. Now, there are planes that go there every so often. Rutland's a tiny town in Vermont, by the way. 8-seater planes go between the two of them like 3 times a day. But just like anybody else who's flying a plane, you have to submit to FAA, and so they've submitted some proposed flight velocity. And the function which describes their proposed velocity, at least what the FAA has received, is this function v of t, which looks like 780t times 1 minus t. If we go ahead and plot that function v, it looks like the following, where in particular you can see I say time in hours is given on the x-axis, but really you should think about that as the t-axis. We've got our velocity in miles per hour. So you can see if we leave at one specific time, maybe half an hour later, our velocity peaks at around 200 miles an hour, and then it starts to go back down. Makes a lot of sense. You're going to, start flying, you're going to increase your speed, but then eventually you decrease your speed. Now I do have this little remark. It may be tempting to think about the plot as a position altitude graph of plane flight. No, this is not describing the altitude. That's just saying we have a high velocity halfway through our flight. Okay, let's answer a question, or really two questions. Supposing we leave Rutland at 12 p.m., at 12:15, where will the plane be? Maybe I'll draw this for you. So maybe here's Vermont, here's New Hampshire, and here is Massachusetts. Looks like a little baby elephant. So there's Rutland, there's Boston, and the plane's just going to go between the two of them. At 12:15, it leaves at 12. At 12:15, you would imagine it's probably somewhere over New Hampshire, but the question is where over New Hampshire? We can answer that using our dynamics, and maybe we could also ask the question, what is the total distance traveled between Rutland and Boston? We could also use that with our dynamics. So let's think about how we would use the velocity that's given here, as well as our initial time being 12 p.m. to actually construct an initial value problem. In particular, we're going to construct an initial value problem for what we're trying to solve, which in this case is position, because I'm asking a question about where and or distance. Both cases mean position. And so I'm going to use the variable s here, and I care about how my position changes over time. How does position change? As well as where do I start? And in particular, for where I start, I can either say, well, at time 12, my initial time, if I'm leaving at 12 p.m., noon. So at my initial time, I start 0, and then I'll use units, miles from Rutland. Useful amount of units. And then how do I change over time? Well, I change based off the velocity that was told to me was 780 times t times 1 minus t. But I have to be a little bit careful, because up here on my graph, if I look at the graph, that starts at t equals 0. In reality, if I'm starting at t equals 12, I can't work with t equals 0 here anymore. I'm going to have to work with starting from 12 and moving forward. And so how do I modify the change, the velocity, to account for me starting a little bit later? Well, I just am going to take that t that was originally here, and I'm going to shift it by 12, as well as my 1 minus t. My t is going to be shifted by 12. And now this will be a perfectly valid velocity, specifically when t evolves after 12 p.m., and we know my initial position takes place at t equals 12 p.m. So this is going to be my initial value problem, or equivalently my dynamics, which will predict the future for me. And then I'm going to want to solve this initial value problem. Now I'm going to solve this. Let's think about what it means to solve it. I have s of t always needs to be equal to my initial position plus the integral from my minimal time up to time t of my velocity. In this case, it's going to be, 780. I'm going to use a new variable u minus 12 times 1 minus u minus 12 du. And in particular, I know what that value is. That value is 0. In particular, I know what this value is. This value is 12. And so that will be the solution as given by the proposition. And then I just have to actually compute that solution. So we can go ahead, go through the little bit of work to compute that solution here. Looks like I use the variable tau here instead. It's all the same. Go through a little bit of work, it's u substitution, and what we end up with is a position prediction, right? This predicts because I've solved an initial value problem. So solutions to IVPs, which are also dynamics, predict the future. So my solution here is saying at time t, at some time in the future, this is the number of miles from Rutland I'm at. So now we can actually answer both questions, because at 12:15 p.m., which I guess corresponds to 12.25 for t, I plug that 12.25 in for t, and I find out I'm exactly 20.3125 miles away from Rutland. So that answers my first question. My second question ends up being answered when I plug in 13 for t, because in fact, if I go back to that velocity function all the way up here, we see that I stopped traveling after exactly 1 hour, but if I started at 12 noon, 1 hour would be at 13 o'clock, whatever you want to interpret that as, 1 p.m., right? So if I plug 13 in for t, then I end up seeing that the distance I traveled from Rutland was 130 miles. And so it ends up being 130-mile travel between Rutland and Boston. We were able to get there by first creating an IVP and then secondarily solving the IVP. Just like with everything else we've done in this entire semester, If we have a continuous situation, we've got a discrete analog to the situation. So in our case, we do have a discrete initial value problem. It's going to look the exact same, except we're replacing our derivative with a discrete derivative. What is the discrete derivative? It's the finite difference. So I just want to write out over here the difference between the two of these, because the other one really looked like d dt of y was equal to f when t was greater than t0, and y at t0 took some initial value x. So I really just want to compare the two of them together. Here's our delta being our discrete derivative as opposed to our continuous derivative. Instead of having f on the right-hand side, we now have a sequence on the right-hand side. And instead of talking about time as the variable t, we're going to use n, meaning, natural numbers, because we have discrete steps of time. And then our initial condition basically looks the same at a very specific starting point, n0. And so everything looks the same. I'm really just replacing the derivative and functions with the discrete derivative or the finite difference and sequences. And I'm going to call these initial value problems, or IVPs, for sums, because the discrete analog to the integral is the sum. And it describes everything the same as before. This first equation describes how a quantity evolves, but it evolves in discrete time, and I care about where the quantity started. The solution is going to look the exact same too, except instead of an integral, guess what we have? We have the discrete integral, also known as the sum. And now let's keep this in mind. We've been seeing this a lot in the discrete cases, that the upper bound on this sum is n minus 1, even though the variable in the solution is n. This happened all the way back when we were doing the discrete calculus as well. It's just something to keep in mind. You can't plug the n itself in for the upper bound. It's always going to be n minus 1. But that's going to be your solution formula. So this, in some sense, being the solution to the initial value problem for sums, is going to be kind of the second formula I want you to memorize for today. And then you just keep both of them in the back of your mind. Really, if you do a good job thinking about the discrete integral as the summation, in particular with the upper bound being n minus 1, you shouldn't have any problem even just memorizing one of the two of these and then being able to translate to the other situation. And so, as always, these are dynamics. I'm not going to go through the proof of that, but they are going to be dynamics in this case. That's why it's in this section. But let's actually see us use kind of an initial value problem for summations applied to a real-world situation. So I really like this real-world situation. I think it's great. So we're going to build a pyramid with a fixed number of blocks. Because you can imagine, I'm going to give you, a specific number of blocks, and I'm going to say build the largest pyramid you can with those blocks. You're going to have to make a decision on the size of the base of your pyramid before you start building. And so you need to predict kind of the total number of blocks that'll end up in your pyramid based off of the base length before you even start building. And that's not going to be an easy thing to do until you realize that you can do it with discrete dynamics. So in particular, in my lovely example, we've got our archaeology department, and they're going to run a laboratory exercise to reconstruct the process of building a square base pyramid as they were built in ancient Egypt. So our archaeology department has 650 total stone blocks which they can use, and they are absolutely stumped as to the size of the base of the pyramid they should start building, because they're going to run out of energy if they get the number wrong. So they've asked us, please calculate the side length of the starting base so that we perfectly use all of the blocks when constructing the pyramid. So we have to interpret this and figure out how to construct a dynamics and then later solve the dynamics so that we can answer this question for them. Well, let's think about a square base pyramid. We're going to start with a square base here. Let's say it's got side length m by m. And if it's square base, then we've just got all of our blocks here. And so what is our initial condition? Our initial condition, meaning at a height of 1, right? Height 1. Our initial condition, we just have a total of m squared blocks we've used. But then let's build up the pyramid. At a height of 2, we're going to offset the bricks by 1 block, right? This is what it means to lay bricks. You always offset them by 1. And so what is the size of the second row? Well, if it's offset by exactly 1, there's going to be half of a brick of no overlap on the left, and there's going to be half of a brick of no overlap on the right. And so we've removed 2 copies of 1/2 of 1 brick. And so our second row is going to have a width of m minus 1 and a height of m minus 1. So I'll say height 2, which means what is the change? How have I changed from my previous to my current? Well, the change in the total number of blocks, which is going to be y, total number of blocks. Well, the change when I've moved upwards, the change in the total number of blocks, if I moved up by 1, is going to be m minus 1 squared. But if I do that again, it's going to end up being m minus 2 squared when I get up to a height of 3. If I do it again, it'll be m minus 3 squared at a height of 4. And then up to the very top where, you could call it either m minus m squared, meaning eventually after a height of m blocks, you're not going to have any left. So 0 squared is going to be your top row. Or you could think about m minus n minus 1, which is just 1 squared being actually the top row. But either way, it's eventually going to terminate at this upper row of n minus n eventually. So that's why we see the change in the total number of bricks is always m minus n squared, because the number of rows that you've moved up, it's that many fewer bricks squared that you need. And so you're adding all those together and you start at m squared. So here's a lovely discrete initial value problem we've constructed, or an initial value problem for sums, that we can actually find the solution to. So let's go ahead and think about what the solution is supposed to be. Solution is given by, well, what did our formula say? It said the solution was the initial value, so m squared, right, so there's my initial value, plus the summation. N starts at this point, the initial time, so 1, and it ends at n minus 1. I should probably use a k as my index here, shouldn't I? So let's go from k equals 1 to n minus 1, and then it's delta yn that goes in here. In particular, what is delta in our case? Delta is m minus k squared. Why have I used a k? That may be confusing. It's got an n there. It's because I want to keep my n as that variable, and I don't want to accidentally get confused over which variable I'm using where. So I'm just going to call the variable I'm actually summing over k here. Okay, so that's going to be what I need to compute, right? I need to compute this. And in fact, to truly answer their question of using all of their blocks, since I said it terminated at m minus m squared, I need to compute this at y sub m in particular, but we'll get to that later. For now, I would just like to compute what is that summation actually going to be equal to. Let's actually see if we can do it. There's my answer, right? Same answer I just wrote down. Let's see if we can actually compute this summation. Well, let's recall what the summation notation actually means. When I write this out, k equals 1 up to m minus 1 of m minus k squared. What does that mean? It means I start at this number 1. I'm going to plug a 1 in. Here it is. And then I'm going to move the number up to a 2, and I'm going to plug a 2 in. There it is. Then I'm going to move the number up to a 3. I'm going to plug a 3 in. I've got that kind of hidden in my dots here. Then I'm going to get up to the top number. What's my top number here? It's m minus 1. If I plug m minus 1 into this, well, that just gives me those two m's canceling, so it's going to give me 1 squared as my very top term. Okay, so I need to calculate. That was coming from the summation. This m squared was my initial value. So what is this in terms of another sum, right? I can use a different summation notation to talk about that. Well, in my new summation notation, I'm just going to talk about summing k squared, where k starts at 1 and it ends at m. So this is really what I would love to compute here. The question is, can I do this? Bob the Builder, can I do this? Bob the Builder, yes I can. I can either use the first power rule for sums going all the way back, but what's going to be a little bit easier is going to be using the second power rule for sums by noting that, well, if you look at k falling factorial 2, that's defined by k times k minus 1, or in other words, k squared minus k, which means that if I just add k to both sides here, add k here, so I can cancel those. You see that k squared is k falling factorial 2 plus k. By the way, k falling factorial 1 is the same as k. And so you find out that k squared is k falling factorial 2 plus k falling factorial 1, which means I can use my second power rule for summation on the falling factorials, and that's just going to behave like an integration power rule, right? You add 1 to the power, you get falling factorial 3, you divide by the new power, you get 3, add 1 to the power, you get falling factorial 2, divide by the new power, you get 2. And then if we remember, how do we evaluate these on bounds like 1 and m? Well, you evaluate on the m plus 1 bound, you add 1 to the upper bound, and then you evaluate on the lower bound as well. And so if I write out what my falling factorials actually are explicitly for both 3 and 2, they look like those. If I evaluate on the upper bound for every case of k here, you end up with this term. If you evaluate on the lower bound for every case of k here, you actually get some zeros, and so the zeros aren't going to matter. Simplify everything that's left. What are you actually left with? You're left with m cubed plus m squared plus m over 6 is the total number of blocks in the pyramid. It's a pyramid of base m and height m. Okay, so then how do we use up 650 total blocks? Well, unfortunately, this is a cubic, so if we wanted to solve, the cubic equal to 650, probably just look up the cubic formula for that. It's like the quadratic formula, but more complicated. But you do get an answer out of this. You get the cubic answer, m equals 12. So you turn to the archaeology department and you say, don't worry, I got you. Make a pyramid of base 12, and you'll use up exactly your 650 blocks. I provided a nice picture of this. There's my pyramid of base 12, and then I'm adding each step to it. And if you are very ambitious, you can go ahead and count the 650 blocks that are in that pyramid. But I'm not going to do that. Let's go with one more example for today. And that example is also a really cool one. I really love the dynamics chapter because everything is so applicable. We're going to ask questions about the length of a roller coaster queue. So you've probably noticed this if you've ever been to an amusement park. The rides are always going to fluctuate in their length of queues. By queue, I mean the line that you're waiting in to get on the ride. So when you assume no ride breakdowns are happening, the rate at which people are able to exit the queue through the ride, right, by riding the ride, it's going to be some fixed number. But the rate at which they arrive is a variable number, right? So there's some function which provides how often somebody can arrive at the queue, but the rate at which the ride is running is basically fixed. So we've got Alice Land over here. Alice Land has a top roller coaster known as the Bobbing Chuck, and it can fit 20 people per coaster. Those coasters run once per minute, so you're getting 20 people through per minute. The arrival rate of riders each minute is going to vary substantially. From the opening hours of 9 a.m. to 5 p.m., the data science team has determined that the riders should be arriving at the Bobbing Chuck on the amount given here, a sub n meaning arrival rate. It's approximately 30 n cubed plus 30 times negative 1 to the n minus 480 n squared plus 1920 minus 240 negative 1 to the n times n. Where this n being in the hours 0 to 8 is really measured as hours after 9 a.m. So we can construct a recursive sequence which constructs the length of the queue at hour n by considering the queue at n is going to be where it was at the previous hour, right? So the queue length at hour n is the previous queue. And then we're going to add arrivals, and we're going to remove riders that were able to ride. And in particular, where did the queue length start when the park opened? Well, it started at 0. Okay, so let's see if we have enough information to actually construct an initial value problem for sums out of this. Well, we're curious about the queue size, right? They want us to know if we can calculate the queue size. Can we calculate the change in the queue size, maybe? And can we calculate where it started? Well, we already know where it started. So we know it's at 0 at time 0. Let's see if we can calculate how it changes over time. We certainly can, because if this is where it is at hour n, and this is where it is at hour n minus 1, if we recall what delta means, delta of qn is going to be qn plus 1 minus qn. And so if we simply add 1 to each case of n here, make it n plus 1, n plus 1, n plus 1, n plus 1, then the n plus 1 minus 1 right here will cancel and give me n, and in fact I could take this entire term and pull it to the left-hand side. What would I be left with? I'd be left with q n plus 1 minus qn, which is exactly delta. So you find out that delta of q is exactly equal to a of n plus 1 minus r of n plus 1. So I'll write that in up here. A n plus 1 minus r of n plus 1. That's what we have below here. I've just gone through and calculated it out. Here is a of n plus 1, the arrivals, right? The arrivals of n plus 1. And then I've subtracted r of n plus 1. Well, r is actually constant here, because we talked about how our roller coaster can ride 60 minutes in an hour times 20 riders gives me 1,200 riders per hour. And so this will be my initial value problem for sums, which I can then go ahead and solve using the formula. Well, what is the formula here? It's going to say q of n is equal to where I started. I started at 0, and I'm going to add the sum starting at k equals 0, because that's my initial time 0, and I'm ending at n minus 1. And in particular, what am I going to sum over? I'm going to sum over this entire nasty polynomial. Well, how can I compute that? You can actually use the rules we've had. It's perfectly manageable. It's not fun to compute the summation of that polynomial. So what I've ended up doing is I've gone ahead and plug this into my computer to actually arrive at the following bar chart, which displays at 9 a.m., 10 a.m., 11 a.m., 12 p.m., 1 p.m., 2 p.m., 3 p.m., and 4 p.m., the number of riders waiting in line. And in particular, we see the maximum number of riders peaking at around 1 p.m., where we have around 3,500 people in line. So we've got to make this line pretty large. This is kind of the information that the parks is asking for us as mathematicians, right? If you work for an amusement park, this would basically be your job, is to predict how long do line basically queues have to be, physical space, so that you can fit everybody who would want to be in line in the line. And in fact, you want them to have a good experience, so you probably need to outfit this line with water fountains, restrooms, enough other entertainment options, so that they're not just standing and bored the entire time. In particular, where does the guest count end at the end of the day? It looks like there are around 600 that unfortunately either didn't get to ride, or maybe the amusement park stays open but just doesn't let anybody else enter the line after 5 p.m. But anyway, that's a quaint little example as well of using, an IVP for sums rather than IVPs for integrals to predict the future. That's all I've got for you today. We're going to move on to separable dynamics, or really separable ODEs, in the next section. I'm hoping you're looking forward to that. See you then. Bye.